Hello and welcome to the second half of Lecture 21, where we're going to continue to discuss sections 10.1 and 10.2 from Young 14th edition. In this second video, we're going to go through a few more complex examples. I'm going to just add some narration to some solutions that I've already written out for these examples to keep the video moving at a good clip. All right, so the first example, we're going to look at example 4. So this one involves a non-uniform density rod. Now it's the same non-uniform density rod that we saw in the set of lecture notes on the center of mass and on the moment of inertia, the most recent set of lecture notes. So in that case, we're going to cheat and just take the center of mass that we found to be 5/9. So in other words, we found that its center of mass is 5/9 down its length relative to the origin that we chose, okay, which you see here is also going to be our chosen pivot point, okay? More on what I mean by that in just a moment. And then we're also going to have our moment of inertia to be 7/18 ml squared, which we got from actually doing the calculus and using our appropriate linear form of our density, right? The density gets twice as dense at one end. In other words, this end over here is twice as dense as the other end. Okay, let's make sure that my internet's off. There we go, no more interruptions. All right, so the thing to consider here is that the actual torque calculation, because what the question's asking is asking for the angular acceleration of this rod, right? If it's free to pivot about that point. Well, if this is going to be the point that it's free to pivot about, if it's attached at that point, in other words, it's free to move, well, that should be our choice of pivot, because that's where we care about measuring our angular acceleration. That is actually where it's pivoting. All right. So in that case, I'm going to use this moment of inertia, 7/18, because that's the moment of inertia relative to that relevant pivot point. Okay. If it was pivoting about its own center of mass, I'd have to use a different moment of inertia, which I'd find with the parallel axis theorem. Okay. But this is the appropriate one for our appropriate pivot. But anyway, my point was that when we actually calculate the net torque, it's quite easy, because we just take the gravitational force, Fg, multiply it by the displacement vector, multiply it by the angle between the displacement vector and the applied force, which in this case is 90 degrees, which actually tells us that our displacement vector is none other than our moment arm, and then set that equal to I alpha by Newton's second law. And then what do? Well, I take Fg, and I rate it as mg, because that's what the force is, okay? I write the location of the center of mass, which I know to be 5/9 L, and then I set that equal to I times alpha, where I is known to be 7/18 ml squared. I simply solve for alpha. We see that the m's cancel, and one of the l's cancel, and then my overall effect then is going to be 5/19 multiplied by 18/17, which becomes 10/7 times 9.8 meters per second squared divided by L, the overall length of the rod, which is 0.45, okay? And so then I end up with an angular acceleration of 31.1 radians per second squared, okay? So a couple things to think about here. One is that the angular acceleration should always be divided by, the units of L, because this is simply saying that alpha has dimensions of A over R, right? Or in this case, G over L. The other thing to consider is that this solution was quite simple, because we had already in previous examples calculated the center of mass and the moment of inertia using the appropriate integrals. If we had any other density function, then we'd have to, from scratch, do the center of mass and the moment of inertia. The reason we need the center of mass, because that's the only place where gravity acts, and the reason we need the moment of inertia, because that's going to allow us to use Newton's second law in rotational form. Okay, so it's as simple as that. So it will always have that. You will always need those two pieces of information. In this case, we just happen to know them, so we could cheat. Yay. Okay. One thing to take note conceptually is that this is a non-constant angular acceleration. Why is that? Why is it non-constant? Well, it's non-constant because check it out. Our angular acceleration is dependent on the angle between the gravitational vector, Fg, and the displacement vector, r. Well, at the moment it's released, right, as shown in the figure, the angle between them is 90 degrees. But what about 1 second later, or 1/10 of a second later? Well, then the rod would have already started to rotate, right? It's going to be now downward somewhat, and the angle between the gravitational vector and the displacement vector is no longer going to be 90. It changes. It instantaneously changes as the rod starts to pivot. Well, that's quite complicated, right? So that means when we talk about angular acceleration for a system like this, for a falling rod or falling beam or something, it's always just going to be an instant in time that we're discussing. Okay, so let's take a look at the next example that I have solved for us. But first, take note, example 5 is left for your practice. It is Very similar to the previous example, except it's a uniform density rod, so you can then determine where the center of mass is and where the gravitational force vector will act. The thing that is different is that now our rod, our uniform density rod in this picture, is not perpendicular to the direction of gravity, and so then when you calculate the angle between the gravitational force vector and the displacement vector, that angle is not going to be 90 degrees anymore. So take note, do that for practice. Okay. So let's take a look at example 6, which I do have a solution, and I want to point out what's going on. So example 6 is quite similar to the example that we did before. Okay, so this is our flywheel and hanging block again. The reason I'm showing this again is I wanted to show how we would calculate tension a bit more. Okay, so taking a look at this, what do we have? Well, one thing is that first of all, instead of giving you a numerical value for the moment of inertia, like in the previous example that was similar to this, that's example 2. In this example, instead, I give you, that was actually example 3. Instead, in this example, I give you a form of the moment of inertia. I tell you it's a cylinder. So that means that we know it's going to have form 1/2 mr squared. That's important because that actually allows for a cleaner expression for the translational acceleration that allows it to kind of look a certain way. So take note of that. All right, let's get into it. All right, so first of all, I write a sum of forces and sum of torques. So I zoom in a tad on this. Okay, so sum of forces and sum of torques. Okay, well, the only object that has relevant forces on it is the hanging block, because that is our only translating object, our only translating free body. Likewise, the torques are only going to apply to the cylinder, which is playing the role of the flywheel, as in example 3. In that case, there's just going to be a torque acting on it, just a single torque, because there's only a single force caused by the tension. I'm representing the tension as T here. Okay. Another thing to take note of is that everything's positive here, or at least the torque is positive because it's drawn on the other side. So the counterclockwise rotation that the tension creates would be a positive. So that's why we don't have the negatives. Okay. And then we do a very similar form. So I'm going then, since initially I don't care about the tension, I'm going to solve for the tension, substitute it in, as you can see here, substitute it into the sum of torque equation. That allows me to write m times g minus a times r equals 1/2 mr squared times a over r. A over r, again, is just that alpha equals translational acceleration divided by radius. Oh, sorry. Alpha equals translational acceleration divided by radius. The other thing to think about is that, remember, that acceleration is the tangential form of translational acceleration. I'm actually going to add a note about that in just a second. So as we then carry on, we're then going to simply solve for a. And notice here, I get an expression where I have mg, right, divided by the total inertia of the system, which is m plus 1/2 big M. Why is there no I in this one, right? Well, because I didn't give you I gave you I as the form of 1/2 mr squared. So then you see that r completely canceled. Check it out, right? Because I had an r over here, which canceled with one of the r squareds, and then I had an r over r because of the substitution of alpha as a over r. So that means that r actually doesn't matter. Well, that's interesting. That means that if we know the exact shape, if we know it's a perfect cylinder, then we know that the acceleration is independent of the radius. Quite fascinating, isn't it? Okay? But what it is not independent of is the actual mass of the wheel, in this case the cylinder. Okay? That mass does matter, and the bigger the wheel, the bigger the cylinder, the slower overall the system will move. Okay? Because it's harder to accelerate that larger object from rest. All right? Or even continue to accelerate it once it's in motion. Now, in part B, just like in example 3, I asked, is the acceleration constant? And I say yes, A is constant, because it's dependent on the constant masses, right? And constant gravity, right? Unlike in the previous example where the angle was changing as the object moved. In this case, there's no angular dependence, and so there's nothing that's going to change as the system continues to accelerate. But there is a caveat here, right? One thing that maybe some of you thought, you're like, wait, okay, yeah, sure, A is constant, but what A do you mean, right? I mean, you're saying that that's translational acceleration, but do note that that is the tangential form of translational acceleration, and that's really what I'm saying is constant here. If I asked you about the overall translational acceleration, the one that is equal to the square root of the translational acceleration squared plus the radial component squared, well, that one is non-constant because the system is speeding up. All right, so that's kind of an important caveat, so I'm going to add that there. So we'll say note. All right, that A, as expressed in this problem, is equal to the tangential form of translational acceleration, and A overall, so A total, which is then equal to the square root of AT plus AR squared, so AT squared plus AR squared inside the root, that one is non-constant, is actually non-constant. Because in that case, AR would be dependent on how fast the system is going, and certainly the system isn't staying at the same speed, neither the same translational speed nor the same angular speed, and so then that centripetal component, i.e. radial component, is going to be changing in magnitude, okay? So it's actually non-constant. So kind of important caveat there, you know? All right. But anyway, so we'll show the part that's new, and that's the tension, right? Well, I mean, it's not a big surprise. If I wanted to solve for the tension, I can just kind of go back and find it, because before I cancel it out. But now I can say, okay, well, the tension is equal to m times g minus a, okay? Or I write here that they have that 1 is equal to I over AR squared, right? So basically that I'm just going to make a substitution, okay? All right, so this just... not a terribly important note here, right? But I don't know exactly what I was thinking, but I'll leave that in there. Anyway, so moving on, then I'm just going to substitute in for the tension, right? Because I've got that I'm going to rewrite the acceleration as, so thus the tension is equal to 1/2 times m of mg over m plus 1/2 m, okay? And then I'm going to make some substitutions in here, and then I get an expression, right? Okay, and then I can get a final answer that this is the form of the tension. And I guess I'm doing that based on this expression up here. And I think that is, oh, I see what this is. And that's why I was confusing myself. That's not a 1, that's supposed to be a t. I think it just, in a copy and paste job, I lost part of it. All I'm saying is that the tension is equal to this, which we already know from our sum of forces, or the tension is simply equal to this that we know from our sum of torques, right? So that's the idea that I'm expressing, simply put, okay? And because the reason it's r squared is because if I was to isolate tension from my sum of torques or net torque equation, then I would divide both sides by r, which would give me an a over r squared, okay? Uncircle everything. All right, so either one, right? I go through all the work of showing that both expressions work. So if I use the first one and I simplify everything, then I end up with a tension that is just equal to mg over 2m, or all over 2m over m plus 1. Or alternatively, I get the exact same result if I use the expression from the sum of forces. Okay, and in both cases, I leave it symbolic because this whole problem was a symbolic problem, right? There's no values given. Okay, so it's all about simplifying things as much as possible and seeing the overall trend of the behavior, right? So you can see then how you can imagine the tension would become bigger and bigger or smaller and smaller depending on the relative sizes of the little m, the mass of the hanging block, compared to the mass of the cylinder, big M. All right, so hopefully that all looks good. Kind of a review from example 3. All right, so let's take a look at example 7. So example 7 kind of plays the role of being an odd problem, right? There's kind of, they fall into kind of categories. You got the the falling beam problem is a common type of simple torque and rotational dynamics problem. The kind of the example of having a block on a pulley or maybe multiple blocks on a pulley would be another kind of canonical example. Well, this one here is a bit odd because we're kind of rolling something up a ledge, in this case a step, and it makes for the geometry to be a bit more complicated. So I just want to call attention to that. So let's take a look at it. So we've got a cylinder. We're given its rotational mass, in other words, its moment of inertia of the typical form, 1/2 mr squared. We're going to take its numerical mass and its numerical radius. They're given, so we can get a number for our final answer rather than a symbolic answer. All right. And then we're told that the step has a height of 0.14 meters. And I asked what value of the applied force F is required so that the cylinder pivots about the edge of the step with angular acceleration alpha equals 20 radians per second squared. So how big must this force be that our cylinder here is going to roll up the step, and it's going to roll up the step at a certain rate? Okay. Well, how do we go about that? So there's two steps. One, calculate the torque of F. That's the subscript there. So that's the torque caused by the external force and the torque caused by gravity, because we have two torques here. Okay. So finally, find the example of multiple torques other than example 1, right? And then we're going to use Newton's second law in rotational form. Okay. So step 1, I'll look at my two torques caused by the two forces. All right. So I have torque F is F times R times sine of phi. Torque G is mg times r times sine of theta. because they have different angles, right? Because we look here, F relative to R is, the angle between them is phi. FG relative to R has an angle of theta, right? Those two angles together make 90 degrees, but they're certainly not the same angle. Also notice that our defined location here, our defined displacement vector R points from the center of mass, because that's where both the forces are applied, to the actual pivot, right? Because the pivot is not the center. The pivot is the edge, right? And it's not just any edge, it's the edge contact with the step. That's kind of the interesting geometry of this problem. Okay, so let's think about it. We need to find phi. So to solve phi, look at the diagram that I drew here, right? This is kind of like the diagram that we'd see for an angled pendulum being released from rest, for example, or a pendulum just at any point in its swing as well, right? So I have that tangent of phi is r minus h over r. Again, consult the diagram. And that allows me to solve for phi as 42.9 degrees for this particular value of r and h. And then finding theta is quite simple because they just sum the 90. And so that means that theta is simply 47.1. Okay, so then I'm going to use Newton's second law in rotational form. Tau net equals I alpha. Then I'm going to look at my two torques. I'm defining my gravitational gravitational torque as positive because it wants to rotate the wheel counterclockwise. Make sure that you can visualize that. And I'm defining my my external force torque as the negative because it wants to rotate the wheel clockwise relative to the pivot. And then that's going to equal I equals 1/2 mr squared times alpha. Alpha is a positive 20 radians per second squared because we're looking for a rotation that's going to be in that positive in the positive direction in the let's see, shouldn't it be a negative? Let's see. Yeah, because I want it to rotate in a clockwise direction. It certainly has a magnitude of 20 radians per second squared. And let's see, I plug in, I'm just checking my my calculations here. So I got the negative there. And then I substitute that from both sides. Subtracted by range. I think this is right. I'm just wondering why I'm not concerned, because I want to create a rotation in that direction, right? I don't want it to be falling back down with an angular acceleration of 20 radians per second squared, because then it'd be falling into the ground, which is not possible. We want it to be rotating in this direction, and that direction is definitely defined as the negative direction, which because that's the sign convention I already started using. Okay. But you can see the approach here. Then I go ahead and solve for 83.6 as my applied force. But if I'd called that negative alpha, or if I had a negative value there, then my tau force would have remained negative. So let's see, because I feel like there is a mistake. I'm gonna go ahead and fix it here during the video. So I'm gonna move this one over as well, because again, our angular acceleration to go accelerate up the step, right? Because I say pivots about the edge of the step with the angular acceleration, and I give you that. I really should have in the problem defined it as negative because I wanted to go up the step. But then these would both be negative values because it's a negative angular acceleration, right? It's going up the step in the clockwise direction, okay? Because that'd be a rotation this way, okay? And that is the negative theta direction, okay? So in that case, if then I'm going to solve for f, I would then have it would be plus, which actually makes a lot of sense that it's plus because they should be adding together, right? So my force needs to do two things. It needs to overcome gravity and it needs to accelerate. And so having a minus didn't make sense conceptually, okay? And so good, actually, I'm glad I'm fixing this. Okay, so then there should be a plus there, which means we have a much larger force, because this force right here would be the force that basically prevent it from accelerating faster than it would otherwise if, say, there was no ground, right? If it was just falling off the edge, that'd be the force of maybe slowing it down as it falls or something. Okay, but that's not the correct value. So I'm glad I fixed the signs there. Hopefully that makes sense to everybody. Let's go ahead and recalculate this real fast with the correct sign. All right, so 12.7 times 9.8 times 0.27, all right, times sine of 47.1. Of course, I'm rounding there because I know there's more significant figures after the 1. And then 0.5 times 12.7, all right, and then times 20. And I'll just divide by 0.27 times sine of 42.9. Okay, so it should be 245 newtons. Good. 245 newtons. All right. Yeah, glad to get that fixed. All right, just missed a negative. Always one of the easiest mistakes to make. But again, hopefully that correction makes sense, and you kind of see why it's so important to pay attention to the to your coordinate system. Okay, and I had to be consistent. Right, I called the clockwise direction negative, which means I had to call the counterclockwise, or I had to continue to call the clockwise direction negative. Okay, and also I should probably be clear here, and again say so the cylinder pivots up the step would probably be a more clear word than about. So we could even say up the step, because that makes it really clear that I'm talking about it going in the clockwise direction. Good. Right? And we could have called the clockwise direction positive, right? And then just called the gravitational force, let the gravitational force create negative torque relative to our pivot being the edge of the step. But I didn't, doesn't matter. Okay, but what does matter is that you're consistent, which I wasn't, so fixed. All right, so that all makes sense. Let's move. Let's look at our last couple of examples. So example 8, I left for your practice. Example 8 is yet another kind of falling cylinder type of thing, right? So it's very similar to example 5, or excuse me, example 6 and example 3. But this one is just make sure that you can do it yourself. So in this case, though, instead of a block hanging from a wheel, it's just a wheel that is falling by itself, okay? I call it a rudimentary yo-yo. So it's basically just like you imagine like winding a cylinder up in yarn or something, and then attaching that yarn to a ceiling, and then just letting the cylinder fall under its own gravitational force, thus unwinding the yarn as it falls. Okay, and then you just need to find the downward acceleration of that falling object. Okay, good. So that'll be a good one for you to practice. Make sure you can set up the appropriate free body diagram and sum of forces and sum of torques. Do note that in this case, the sum of forces and sum of torques are both going to be for the same object, for the rudimentary yo-yo, because that is the only object in the system. It's a single object system as opposed to the previous two examples. And then, as such, it's going to be both translating and rotating. By the way, that's kind of foreshadowing things to come, because in the very next lecture, so that's going to be in lecture 22, that's all about objects that are translating and rotating, which are rolling objects. Because technically, a yo-yo is a rolling object. It's just vertically rolling. But I kind of included it in this lecture as a segue, because we don't necessarily think of yo-yo as rolling. And so it kind of made sense to have it be that transition. All right. So, but again, good for practice and a good bridge between lectures 21 and 22. All right. Of course, you'll see lecture 22 on Wednesday. So the last example I want to show you is example 9. So example 9 is kind of the whole kit and caboodle. In this case, I have a hands-on lab that I've done at schools in the past. And in this, it's a lab where we can measure the moment of inertia. We basically have a large platform. Okay, so let me read it. So in a laboratory experiment, an apparatus is constructed that uses gravity acting on a hanging mass to turn a pulley that then turns a spindle that then turns a large iron plate resting on the spindle, right? A lot of and then, right? And then, but then there's more, right? But wait, there's more. The system is assumed to have no friction or other non-conservative forces. The hanging mass has a weight of 15.5 newtons, okay? Well, we'll have to turn that newton into a mass, right? The pulley has a diameter of 6 centimeters. The mass of the pulley, m sub pull, has a mass of 80 grams or 0.08 kilograms. The spindle has a radius of 5 centimeters, and the mass of the spindle has a mass of keep repeating myself. The mass of the spindle is 0.2 kilograms. And the disc, finally, has a radius of 24 centimeters and a big old mass of 5.8 kilograms, right? Because the disc is massive. Of course, the disc is the big thing on top, right? This is the disc up here. And so then all rotating objects are considered to be cylinders, right? So they're all going to have a moment of inertia of a form 1/2 mr squared. And finally, the only question, although I call it part A, but the only question is, what is downward acceleration of the hanging mass? So the whole idea there is that, one thing leads to another, right? There's the driving force, the single driving force is gravity, right? Because that gravity and depending on how quickly the hanging mass is going to accelerate, is going to create a tension. That tension then is the tension acting on the pulley is then going to create a tension that acts on the string connecting the pulley to the spindle, and then that tension is going to spin the spindle, and then resting on top of the spindle is a large rotating mass. Okay, so one thing to note here is that the tension on this side of the pulley is not equal to the tension on the other side, because of course they're not equal to each other, because in between these two forces is mass. Now, when we had massless pulleys, think Atwood's machine, in that case the tension on both sides of the pulley were equal because the pulley was assumed to be massless. But anytime the pulley is not massless, the tensions on both sides are absolutely not equal to each other. Just like if we were pulling multiple blocks down, or along a horizontal path, the tension between each connecting string of those blocks all being pulled together in a chain would all be different. Okay? Just like the tensions between each car and a train are all different, because they're dependent on, what's the inertia between each connection. Okay? It's all about Newton's third law, really. So let's think about our full kind of sum of forces and sum of torques here. All right? So I have a sum of forces on the pulley, which is going to be Fg minus T, and that's on the hanging mass, actually. Why do I call it the pulley? I guess I could, I don't know. I'll change the subscript. This is really hang, right? There, hang. Okay, so the sum of forces on the hanging mass in the y direction, defined with positive y defined as downwards, positive theta defined as counterclockwise. Okay, so kind of consistent coordinate system there, except I'm calling positive y downwards. And I have then that Fg minus Tp equals Ma. Okay, makes sense there. Notice that Ma is positive because I'm calling downwards positive. Then I look at the sum of torques on the pulley. That's that one right here. Well, the pulley has two torques acting on it, right? It's got a torque created by the tension, Tp. That's the tension that is shared by the hanging mass and the pulley. And then it's got another torque that's created by the tension that's shared between the pulley and the spindle. That's T sub s. Okay? All right. So then that's going to be equal to I pulley times the angular acceleration of the pulley, which is alpha pull. Then I've got the sum of torques on the spindle. Okay, so let's think about that. Well, the sum of torques on the spindle is simply going to be a single torque, because there's only one force acting on the spindle, which is the tension that is shared by the spindle and, let me use this highlighter here, by the spindle and the pulley, right? Because the string, this is massless, so that tension can be shared, right? Because again, the tension remains unchanged as long as there's no mass in between. Okay, so, but here's the thing. That's going to be equal to I times alpha, but it's not just I of the spindle, because sitting on top of the spindle is this big giant disk. So the inertia that actually is relevant to the applied force, Ts, is the overall inertia of the spindle plus disk resting on top of it. So it's 1/2 m spindle times radius squared plus 1/2 m disk times radius of disk squared. Okay? So that's the overall inertia. That's what these parentheses represent. And that's going to be times the angular acceleration of the spindle. All right, so a couple things to think about. Well, first of all, we have that the angular acceleration of the pulley is going to be A over D, A divided by D over 2, because D is the diameter of the pulley. And the angular acceleration of the spindle is just going to be A over R. Okay? So that's going to be the relationship between our two angular accelerations. Are those angular accelerations equal to each other? Absolutely not. And they don't have to be equal to each other because they're both dependent on radius. So if the spindle and the pulley have different radii, then you better expect they're going to have different angular accelerations. But you know what is the same? A, right? Why must the tangential component of the translational acceleration of the hanging mass be shared by all of the other objects, all the rotating objects? Well, because the string is not stretchable, because it is an inelastic string, and a massless one at that, or cord, or whatever you want to call it. For that reason, the A value, the translational acceleration, is shared, because there's no other way, right? You can't have this hanging mass, moving down faster than its perimeter of the pulley is spinning, or then the perimeter of the pulley is spinning, because otherwise the string would have to be changing length, wouldn't it? And you can't have the perimeter of the pulley moving at a different rate than the perimeter of the spindle, because if they were moving at different rates, then the string here, our massless connecting string, would have to be either becoming shorter or longer. And if it's inelastic, unflexible, completely rigid, effectively, then That can't happen. It's impossible. Okay? So that's why we can be confident that A is shared by everything. It's really the one thing that is shared in this problem. Okay? So at this point, it's just a bunch of algebra. You can see that I go ahead and solve for the tension shared by the spindle and the pulley. In terms of the values of the masses and the radii, I get the following expression here. Then I do the same sort of thing for the tension shared between the hanging mass and the pulley, T sub P, which I set up here. All right, and I continue to simplify things, cancel out a lot of the radii, and so then I get the following expression for the tension there. Then I'm going to substitute those two values back in. All right, so you can then I'm relating them here. So basically then I have, or I'm going to at least start by substituting the tension shared by the hanging mass and the pulley. That's what this is right here. And I set that equal to MA. Okay, and then what do I do for, okay, then I can go ahead and solve for A, which I go ahead and do here. Actually, I don't think I'm really going to do much with, what do I do? Oh, that's right. So the reason I do this first step in solving for the tension is because my overall kind of my guiding equation, the one that I'm using the most is this one right here. Because this is the one equation that has both tensions in it. So that's the equation that I use. Okay? Yep. Good. And so if you look at where I really substitute in the values, that's how I'm going to connect everything together. Okay? And so then finally I get an acceleration for the acceleration of the falling block, and we can see that it's up in the numerator, there's just mg because that's the driving force, and then down in the denominator is the overall inertia of the system, right? It's got the mass of the hanging mass, okay, and then plus we got 1/2 mp plus 1/2 ms, and then plus this expression here, okay? Why does this one still have this ratio of r over r? Because the string is not wound around the outside of the disk, so the radius of the disk matters, okay? The radius only cancels out when the torque and the moment of inertia share a radius. Well, as far as the disk is concerned, the torque and the moment of inertia don't share a radius. So anytime your rotating axis is different than your inertial axis, the radius will not cancel out from your final result. Okay, but in this case we had all values, so I can plug them all in, and when I do, I get an answer of 0.226 meters per second squared. So good one for practice, kind of big example, connects a lot of ideas. Make sure you look over my solution and make sure it makes sense to you and you can do it yourself. Okay, so that concludes